And, well, another announcement is that the NSF recently announced a new math institute on the east coast of the U.S. In Providence, which just announced yesterday. So we're, since I'm part of the organization of that math institute, we're soliciting programs for the future years. If you have some interesting idea about a probability program or other area, you can either talk to me or, well, it's so new that they don't even have a web page up yet, but there's a lot of money and a lot of opportunities for research on the East Coast in the Northeast. So either talk to me or look at the web page. I'll write down the web page on the board. Greg has an announcement too.
What's the name of the institute?
Nice, sir.
Well, actually, the next.
Okay. Institute for Computation and Experimental Research in Mathematics. Did you get that?
Just say Brown. That's probably more important.
Computation and experimental. So, Brown University.
Okay. Another announcement, which is really both of us. So while he's doing that, in spring semester, so approximately January through May of 2012, there will be a special semester at the MSRI at Berkeley on, various things, but probability and statistical mechanics, both computational and analytic and conformal invariance techniques, a number of things through the year. We're just now getting the process of actually getting the exact dates for workshops and things, but there's going to be money available for postdocs and for senior people, at least to support visits, maybe not for, not for salary, but for to support local expenses and things like this. For salary for postdocs. So be on the lookout for that's MSRI at Berkeley. And actually Rick is the chair of the organizing committee. I'm only a peon on the organizing committee. But, but we're both involved. And just keep alert for that. And if you can't, if a few months from now you start getting interested and you can't remember where you can't find anything, just email either Rick or me and we'll get in touch with you. The other thing I wanted to say is that I did actually fulfill my promise to finish my lecture notes from last week for those who are interested. Not sure it's actually gotten posted on the Clay page yet, but you can take a look for it. I'm leaving today. If you're really, really dying to have it immediately, you can get it if you bring a memory stick, and you can take it from my computer over lunch period like that. If not, if you just want to wait a few weeks anyway, I will actually post it on my homepage at Chicago, but that'll probably take a couple of weeks. Oh, they are up. Yeah. They weren't up as of an hour ago. So they're up now, okay. So you don't have to catch me. Yeah. No.
So today's a bit like going to the cinema before the show starts. There's a lot of advertising. And I have one of my own, which is that at UBC in Vancouver, we're always looking for postdocs in probability. And this year also there's a tenure track position in probability, so many of you may be looking for such positions. You can go to Math Jobs and find out all of the information at that URL there, or you can ask me. Okay, so today I want to talk about something quite different from what I've been talking about over the last 2 days. No more LACE expansion, so if you don't remember all of the estimates from yesterday, that won't be a problem. And there won't be any estimates, I guess, today. I'll be talking about identities. And the content of what I have to say is contained in a paper with Bridges and Imbrie that appeared in Probability Surveys last year. And there's lots more in that paper than what I'm going to talk about. And the topic is integral representations for the self-avoiding walk. So these are identities which take self-avoiding walk model two-point functions and rewrite them in terms of certain functional integrals. And these integrals involve anti-commuting variables, or fermions, which show up in these representations simply as differentials. So they're not, these differentials do end up forming a Grassmann algebra of forms, differential forms. But you don't need to know a lot about forms in order to understand what it is that I'm going to be saying today. The representations are valid for self-avoiding walks on a finite set. Now, we're interested in applying these representations to, and they have been applied and are continuing to be applied in studying four-dimensional random walks, so on z to the 4 or on hierarchical four-dimensional lattices. And in order to make the transformation from the finite set to the infinite lattice, you need some theorem that tells you that the infinite volume limit does the right thing. And that can be achieved using a kind of standard technique in statistical mechanics that sometimes goes by the name of the Simon-Lieb inequality. And that will be the topic of today's tutorial this afternoon. So if you don't already know about that, then this would be a good opportunity to learn about it. It's not something that applies only in the context of self-avoiding walks, but it's useful also in spin systems where it originated, and it works in percolation as well, and it's just a good thing to know about in general. So today I'm going to be talking about self-avoiding walks on a finite set. You should think of this finite set as being really extremely large. You know, it has 10 billion points in it or something like that, and our self-avoiding walks will be living in this set. And in fact, it doesn't even have any structure. It doesn't have any geometric structure, even though the sets that I'm interested in would be periodic approximations to z to the 4th. So tomorrow, when I discuss how to use the renormalization group in conjunction with these representations, the set that the walks are living in will be a four-dimensional lattice torus, discrete torus. But today, there's really no structure to this set, and in fact, the walks are allowed to step from any point where they're located to any other point. There's no geometry, and there's some weight which is associated to these. Okay, so I'm giving you a bit of a preview of what's coming. Now, in order to start off, I need to talk about some basic things regarding Gaussian integrals, finite dimensional Gaussian integrals. And many of you will be familiar with these Gaussian integrals already, although I'm going to be talking about them in complex Gaussian integrals, and maybe there'll be some something of interest there. So the topic that I start with is just Gaussian integration. These are finite dimensional Gaussian integrals. And there won't be any self-avoiding walks or random walks popping up for a little bit, but they will show up. So you fix some integer m, positive integer, which is very large. It's the cardinality of this four-dimensional torus, for example. But for the moment, my set of points is just 1 up to m. And I want to define a two-component field. In physics, this would be called a bosonic field, which just associates a complex variable to every point from 1 up to m. So my points are labeled from 1 up to n. There'll be a subscript x, which is telling me which point I'm at. And I have a complex variable living at each point. So you can think of it as a spin, if you like. For the moment, we could consider just the real and the imaginary parts. So here, x and y are living in, x rather, is living in 1 up to m. Okay, so the subscript x, I'm using the subscript x as the index rather than I or j because ultimately I want to think about x as being the location of a random walk. And ux and vx are in R. The real and imaginary parts, I want to make them of a complex field. So what's the complex field? I just define phi of x to be ux plus ivx. I is the square root of minus 1. And as usual, there's a complex conjugate. Phi x bar is ux minus ivx. So at each point x, I have a complex variable, and I want to associate a differential to that. So there's going to be a differential d phi x, which is dux plus I dvx. And there'll be a d phi bar x, which is dux minus I dvx. And I want to multiply differentials using wedge product. Now, if you're not familiar with wedge product, then don't worry. It's not going to play a very big role. The only thing that you need to know about it is that it anti-commutes. So it's just a way of keeping track of the order that you write the differentials down. D phi x bar wedge d phi x is equal to minus d phi x wedge d phi x bar. And what this is you just do this product here. So you'll get dux wedge dux. It's use linearity plus dux wedge I dvx minus I dvx wedge dux minus I dvx wedge I dvx. And because it's anti-commutative, the square is always equal to 0. Dux wedge dux is equal to minus dux wedge dux. So it vanishes. These cancel out. This one can be reversed. And so what I end up with is 2 times I dux wedge dvx. And so this is just going to be a convenient way of putting together these sort of Lebesgue measures, dux and dvx. Now, let's suppose that C is an m by m complex matrix. And I would like it to have a positive definite Hermitian part. So I'll say what that means. These matrix elements are ultimately going to be the weights associated to steps of the random walk model. So what it means is that if I sum over x and y from 1 up to m of phi x times the Hermitian part of C, which would be cxy plus cyx bar, phi y bar, that this should be greater than or equal to 0 for all, well, I wanted greater than 0 actually, for all phi which is not equal to the 0 vector, the m component 0 vector. Okay, so it's a got positive Hermitian part, and then it's easy to see from that it's invertible. And we'll be making use of this inverse matrix. In fact, it's so useful that we'll give it a name and write A for the inverse of this matrix C. Now, given this matrix, we can define the Gaussian measure that has that covariance. So the Gaussian measure with covariance C is the following. It's d mu C of phi and phi bar. So phi is the vector with components phi 1 up to phi m, and phi bar is its complex conjugate. This is defined to be 1 over a normalization constant, z, that depends on this matrix C, of e to the minus phi a phi bar d phi bar d phi. Now, what do I mean exactly by the things that are showing up here? So there's 3 undefined quantities. There's d phi bar d phi. There's phi a phi bar. And, well, I haven't said what the normalization constant is, but the name kind of gives it away. So what are these things? First of all, d phi bar d phi, by definition, the order matters as to how I write these differentials. And it's going to be d phi 1 bar d phi 1 all the way up to d phi m bar d phi m. And I'm not going to write the wedges anymore. Okay, but the differentials are always multiplied by wedges. It just means that I care about the order, and if I interchange two adjacent differentials, then I would change the sign. So for example, if I keep the phi bar and phi factors together, it doesn't matter what order these subscripts would be in, because that would correspond to an even number of interchanges, and the overall effect would be +1. However, if I were to interchange the d phi and the d phi bar in each factor, then I would get a factor of -1 to the m. So that's the way I'm organizing these differentials. And then the phi a phi bar is just shorthand for a kind of matrix product. So this is the sum over all x and y from 1 up to m of phi x times axy times phi y bar. And z is the normalization constant. So zc is the integral over R2m or Cm of e to the minus phi a phi bar d phi. So if you integrate this Gaussian measure over c to the m, then you end up with 1. It's a normalized measure. You can write it in terms of real variables as well, because these products, d phi bar and d phi, are just du and dv. Now, you can evaluate this zc explicitly. So here's a little lemma that tells you what its value is. This zc is equal to 2 pi I to the power m divided by the determinant of a. That determinant is non-zero because A is an invertible matrix. Its inverse is C. And that's what it is. And it's actually easy to prove in the case when C is actually a Hermitian matrix, and then A would be a Hermitian matrix as well. In the more general case, you have to worry about the anti-Hermitian part, but that doesn't really cause any grief. I don't want to discuss it. So let's just talk about the proof for the case where C is Hermitian, where this is relatively easy to prove. You see, if C is Hermitian, then so is A, and you can diagonalize A. By writing it as A equals U inverse times some diagonal matrix times U, where U is unitary. Then you can rewrite the exponent phi a phi bar. And here I have to get it right. So it's rho d rho bar, where rho is u bar times phi. Okay, so that's matrix multiplication. U is a matrix, u bar is a matrix, phi is a vector, and I'm just multiplying them together there. And then what happens is that up here in the exponent, now that it's written in terms of this diagonal matrix, it factorizes. And the differentials also factorize. There's some Jacobian that pops out, but it's 1. Oh, I wrote on the wet board. This is here forever. So once you make that change of variables, what you find is that this integral factorizes into a product, x equals 1 up to m, of the integral over R2 or over C, but I'm going to rewrite the d phi bar d phi in terms of du dv, of e to the minus dx. I mean, the d phi bar d phi becomes d rho bar d rho. Dx, the diagonal entry of the matrix, ux squared plus vx squared times the 2I from the 2I in the d phi bar d phi, dux dvx. So that's what it becomes. It just simply factorizes into a product of m two-dimensional integrals, which are just the integrals that show up in the normalization of a usual and one-dimensional Gaussian. And so you can do these. And what you find is that you get 2 pi I to the power m. There's already the 2i sitting there m times, and there's some pi's that come out from the integral. And there's also a product downstairs over the x's of, this d should not be confused with the differential, right? This is the entry of the diagonal matrix. So you get the product of the entries of the diagonal matrix, which is actually the determinant of your original matrix A. So that proves the result in the case when you can do the diagonalization. It's not difficult to extend it to the more general case, and I won't discuss that. Yes?
So you say you're no longer writing the wedges, but if you turn this thing around, you get minus signs. How do I see that? Because now you're just seeing it as a normal.
Yeah, that's right. So when it's du dv, then it's the right order to give me a +1. That's my convention. Now, there are also complex derivatives. So you can differentiate with respect to phi x. And that is just defined as 1/2 d by dux minus I d by dvx. And you can differentiate with respect to phi bar as well. These are definitions. 1/2 d by dux plus I d by dvx. Why are these good definitions? Well, it's easy to check the following identities then follow. D by d phi y, d phi y by d phi x, rather, is the same as d phi y bar by d phi x bar, and that will be 1 if x equals y, and otherwise it will be equal to 0. So it has nice behavior that you would expect for differentials. And if you do them backwards, or not backwards, but if you mix and match, then you get 0. So it's easy to check that any one of these is true. You know, you just plug in phi y equals uy plus ivy, and you check, and you see that it works. So I won't do that calculation. It's really very trivial. Now, something that we're going to make good use of is integration by parts. And this next lemma discusses integration by parts in this context. So here's the form that we're going to do integration by parts. There's some hypothesis about the kind of integrands that we can have. Let me just say, if it's nice enough, a nice enough function f, which is a function of phi and phi bar, or you can think of it as a function of u1 up to u1 up to um and v1 up to vm. It's some function like this. Then the integral of phi a bar, so a is a point, a value from 1 up to m, times f d mu c of phi bar is equal to the sum over x from 1 up to m of cax times the integral df by d phi x d mu c of phi bar. So f nice enough basically means that it's good enough that the integrals on both sides exist. So it shouldn't be growing so fast at infinity that you can't integrate it against the Gaussian measure. It could be growing exponentially. That would be okay. So how to prove this? Well, we'll start with the integral on the right-hand side because it looks like the right kind of thing to do integration by parts with respect to, right? I mean, when you do integration by parts, you want to have an integral that has a derivative in it, and you want to move the derivative to the other part of the integral, and that's what we want to do here. So we'll start with that df by d phi x d mu c. And we want to write this as 1 over zc, which is the normalization that we just computed over there, times the integral of df by d phi x e to the minus phi a phi bar d mu c. And now this is just an ordinary integral. Thank you. This is just an ordinary integral once you write it in terms of du's and dv's. And you can apply ordinary integration by parts to move the derivative off of the f and onto the exponential. And we know how to differentiate with respect to phi x because we have these sorts of properties that are holding here. And that d by d phi x, once it gets moved over onto the exponential, is just going to be integrating the phi part, which is up in the exponent. It'll treat the phi bar part as a constant, and a is a constant. And so when you do that, you'll get, by ordinary integration by parts, minus sign. So this is just ordinary integration by parts, times the integral of f. There won't be any boundary term because things are vanishing at infinity. F is nice enough that that happens. This is very small at infinity. Times the derivative with respect to phi x of e to the minus phi a phi bar. And, well, phi a phi bar is sitting here, and so when we differentiate, what we'll pick off is an a and a phi bar and a sum. So this derivative here is going to be minus the sum over y of axy phi y bar times e to the minus phi a phi bar. And so what we end up with after doing this is 2 plus signs, 2 minus signs, so it corresponds to a plus. We get the sum over y, axy, times the integral of f e to the, well, times d mu c. And, oops, there's the phi bar that came down. Phi y bar times f times d mu c. It's not quite what we want because now there's the summation, which is sort of on, summation is on the wrong side, but it's with respect to the inverse matrix. So then you simply apply the inverse matrix to each side of this equation, which is C, and you cancel out the A that you don't want and produce the C that you do want. So now you take the sum over x of cxy times this expression. No, I guess not. CAX is what I want, right? CAX, yes. So apply that to both sides, and on the left-hand side, I get the right-hand side that I'm after. And on the right-hand side, the C's and the A's cancel, and y gets set equal to A when I do the matrix multiplication and produce the identity. And this is what we get. So it's really just standard integration by parts dressed up a little bit. And what it allows you to do is when you have an integral which involves an explicit factor of phi a bar, you can remove that, differentiate what's left of the integrand, and the price is that you end up with this kind of convolution appearing with the covariance. Now, in particular, if you take f to have a very simple form, the simplest interesting form, which is to take f to just be phi sub b, you see that the integral of phi a bar phi b d mu c, what's that going to be? Well, this is the f. And so the phi a bar is going to disappear and differentiate the f. When it differentiates the f, you'll get a Kronecker delta. There's that sum which is still there. And so in the end, this is just CAB. So it's behaving as it should for the covariance of a zero mean Gaussian variable. It's giving us the covariance. You can calculate other kinds of moments, and we'll want to do that. Let me state a lemma that will be useful for us. This is a special case. I mean, there's nothing to stop us from going into a more general case than what I'm going to say right now, but this is all I'm going to use, so I'll stick to that. It's a special case of what's called Wick's theorem. Many of you will be familiar with that. And it says, let's suppose that I'm given distinct indices x1 up to xm. And so the x's are distinct and the y's are distinct. So let these each be distinct, be sets of distinct indices. I don't care if an x is equal to a y, but I don't want two x's to be the same, and I don't want two y's to be the same. This is where the special case comes in. The more general case would not have such a restriction. Then, suppose I want to compute the integral with respect to this Gaussian measure d mu c of the product from I equals 1. I don't want to go up to k. Sorry, I don't want to go up to m. There's only m variables around. I don't want them all. So just go up to some k. What might be equal to m, but it doesn't have to be. Phi xi bar times phi y I d mu c. So I'd like to calculate a moment like that. Previously, I was considering the case k equals 1, but now I have a larger product. What's going to happen? Well, we've got the integration by parts. What the integration by parts is going to do is it's going to turn a phi bar into a derivative and pick up a c along the way. And, well, the c, there's not going to be any sum because there's a Kronecker delta that comes in the same way that it did in this very special case of k equals 1 that we just looked at. So when I want to integrate by parts with respect to phi bar x1, what it's going to do is it's going to look for phi's to differentiate. And it'll pick one of the phi's in this product and differentiate it and produce a covariance, and that will be the end. But then I can move on to phi bar x2, and it will go and look for a phi to differentiate. It'll find one, differentiate it, and then stop. And this can happen in many ways. In fact, you see what happens is that there's going to be a sum over the ways that you can permute these phi's to assign them to the phi bars in order via this integration by parts process. So the formula is the sum over permutations on k letters of the product over I from 1 up to k of the c sub xi and then sigma of xi. Sigma of yi, I should say. Okay. So I hope that's clear. It's just the proof is just what I said. You integrate by parts repeatedly. Each time you integrate by parts, the phi bar looks for a pi to pair itself up. Looks for a phi to pair itself up with, and each time that pairing occurs, you get a covariance, and you're going to get it in all possible ways that you can do those pairing ups, and that would correspond to the number of ways that you can form permutations of the y indices. So that's the proof. Integrate by parts. Y of sigma I. Thank you. Right. So this looks like a permutation. but there's no signature. There's no sign of the permutation occurring here. And so when that's missing, it's called, it's not a determinant, it's a permanent. It's the permanent of the submatrix of C, which is indexed by the x's and the y's. All right, so we can calculate those kind of moments, and that's going to give us a random walk representation. So I want to suppose I have a finite set lambda now, which you should think of as being 1 up to m. I'm numbering the points. There's some typically large number of them, although it works also if m is small here. So you should think about, say, lambda as being a subset of Z4, maybe a periodic subset, so it's not, so there's a torus, perhaps. And I want to fix two values a and b in lambda. And then I want to fix some subset of lambda minus ab. Actually, usually x just is lambda minus ab. So I want to look at all of the other points that have not been singled out with this identification of a and b. And now I want to consider the following integral, which I'll call g sub ab, which is already starting to look kind of like a two-point function. It's the integral of phi a bar phi b times the product over x in x of 1 plus phi x bar d mu c. And basically what I want to do is I just want to evaluate this integral. And once we've evaluated it, you'll see why I wanted to do that. Should be no problem to do the evaluation because actually we've got a formula over there for evaluating products of phi's and phi bars. And you know, if you were to expand out this product over x, you just have a sum of terms of that type. So this shouldn't be so challenging. Let's see what's going to happen. Here I will write the set x like this. And a is some point which is not in x. And b is some point which is outside of x. And then there's a bunch of points which are inside x, typically quite a few. I want to start with this phi a bar and to perform integration by parts. So I'm not going to expand out the product just yet. So what is this phi a bar going to do when we apply integration by parts to it? It's going to disappear, and it's going to differentiate some phi, a phi. It's going to look for a phi to differentiate. And well, there are many phi's that it can find. It could find this one, or it could find one of the ones in the product over here. Let's suppose it found that one. If it found that one, then what it would do, it would be to produce a factor CAB, a covariance CAB, and then these would be gone, and we would have this other integral left over. That CAB I want to think about as being a random walk which goes from A to B in a single step and carries that weight CAB. So the covariance entries are going to weight steps of walks. So that would be one contribution. Of course, then there'd still be this product to deal with. But when phi a bar is doing its integration by parts thing, it might not find the phi b right away. It might go instead and differentiate a phi x which is inside this product. Call that a contraction. Phi a bar would contract with a phi x in the product and produce a CAX. And it would eliminate that factor from this product, and it would leave behind as a residue the phi x bar corresponding to the x value that got differentiated in the integration by parts. And then what would happen would be that phi a bar would be gone, phi x would be gone for that particular x, and the corresponding phi x bar would be like a new phi a. So what will happen is that x which got picked, maybe it was this one, would correspond to a step from A to X, which would be weighted by the covariance entry CAX, which is produced in the integration by parts. But now this point becomes the new A, and it just happens again. And it's eliminated. That point has been eliminated from X in the sense that it no longer sits in this product because that corresponding factor has been disappeared by the integration by parts. And so you end up with self-avoiding walk path from A to B, because ultimately what will happen is that this phi b is going to get differentiated by somebody. After the integration by parts is done enough times, this phi b will be found, and it'll be gone, and they'll be left. So this is not the end of the story, this self-avoiding walk, but the self-avoiding walk will be produced in all possible ways from A to B, weighted by the corresponding covariances of entries along the steps, and then there'll be left some product of the undifferentiated stuff afterwards. So what I claim is that this is supposed to be convincing you that GAB is equal to the sum over all self-avoiding walks from A to B that take their intermediate steps in X of C to the omega. I'll write it that way, and I'll explain what that is. Then there's the remaining integral of the factors that didn't get found in that particular integration by parts process that produced the walk omega. So there's going to be a product over X in X minus omega, that's the vertices of omega, of 1 plus phi x bar d mu c. So what is this c of c to the power omega? This just represents the product over the vertices of omega of c omega I minus 1 omega I. So I hope that I've convinced you about this. Is there any question about that formula at this point?
Are all the front phis gone when you reach B?
Yes, because I started with this one, so it'll disappear at the first step. And this one will be gone when I reach B, because I will differentiate it. And then somebody will be left over, typically. Maybe not. I mean, if it was a space-filling curve, then there'll be nothing left over. But typically, there'll be something left over. So this is not quite a self-avoiding walk model because, well, we do have the self-avoiding walks come in, and we're very happy about that. But then there's this other factor, and we have to figure out what that is. But we can evaluate that, too. We've got Wick's theorem that allows us to evaluate anything that we want in terms of products of phi bars and phis, and that's exactly what we have here. So let's look at that product. So I want to now consider the product over X in some subset Y of our original lambda. In our case, it's going to be this X minus omega, but it could be anything for the moment. 1 plus phi x bar d mu c. They're self-avoiding because each factor only appears once. Once it's differentiated, it's gone. It's vertex avoiding. There's no structure. There's no structure. I mean, I've drawn lambda like a grid, but it's not a grid. It's just a set of points. And so but you will never get this. This kind of thing will never. There's no loops. Yeah, I don't care about that. Yeah, right. It's the vertices avoid. No vertex is repeated. That's what I mean by a self-avoiding walk here. The edges exist kind of only in our imagination anyway. You know, there's no geometry. Yeah. So yeah, I mean, this can happen, but I'd still call it self-avoiding. But the picture's meaningless in that sense because there's no structure to X. It's just a set of points. Okay, so let's compute this. So I need to take the product. If you went to the first tutorial, and maybe even if you didn't, you're already an expert in taking such products. So what you do is you want to sum, you're taking a big product of factors of 1 plus something. You want to just choose all of the ways that you could pick this factor and multiply together. And that corresponds to choosing a subset of y. And what do I want to call that subset? Z. How about Z? OK, so Z is an index labeling subsets of y. And then I have the integral of the product over x in Z of phi x bar d mu c. That's just what happens when you multiply out the product. And now Wick's theorem over there tells us the answer that each term in that sum is a permanent. It's a sum over permutations of factors of c. So this becomes equal to the sum over z in y of the sum over permutations of z of the product over x in z of c sub x and then sigma of x. I've just used Wick's theorem. Here the set of x's happen to be the same set as the set of y's, but that's fine. Now, I want to decompose this into cycles. So the permutation decomposes into cycles. And this product factors over the cycles. So I'll have one product for each cycle as we just run around the cycle. And so what that means is that once you take this integral into account, you can represent it pictorially. Let me draw another picture here where, so what I claim is that GAB corresponds to a sum of configurations like this. Here's X, here's A, and here's B. So there's going to be a self-avoiding walk that goes from A to B. Each step is weighted by the corresponding covariance matrix element. But then what these cycles do is they're going to produce loops like this, maybe loops that just link a point to itself. If you have a fixed point of your permutation, the cycle would be trivial like that. And you can either have these or not. So there may be points that don't have anything. But what this is producing is a sum or a generating function, if you like, for self-avoiding walks from A to B, taking their steps inside X, with each step weighted by the corresponding covariance matrix element, with a background of self-avoiding and mutually avoiding loops, which are also weighted each step by the corresponding covariance matrix element for that step. CXX, right. This is CXX if that's X. And there can be empty places here, okay, because of this sum over Z. The points in Z are going to be the ones that participate in the loops. But you're summing over all of the Zs, and sometimes there's stuff left out of that's not in Z but is in X. So that's kind of an interesting representation. It's not what I want, though, because I don't want loops. I mean, there's lots of interesting loop models, and we've heard lots of things over the last 4 weeks about loop models. They're fun to study for sure, but I don't want to study them right now. I want self-avoiding walks only, so we have to kill the loops. So that will be done using fermions. So the next topic is differential forms. And if what I've been talking about up until now is bosonic Gaussian integration, we're going to have mixed bosonic fermionic Gaussian integration. So fancy name. Okay, so that's the next topic. And now I have to pay a little more attention to this wedge product. So I want to think of what's called a Grassmann algebra. Actually, I don't think I'll use this term anymore, but it's kind of a standard term in physics when people are studying fermions or anti-commuting variables, and so I might as well use it here. But what I'll be talking about is just differential forms. And if you're not very familiar with differential forms, then don't start thinking about something else yet, because they're fairly simple in the context that I want to be talking about. So it's an algebra which is generated by the differentials, which we can think of either as in terms of du's or dphis and dphi bars. It doesn't matter. I'll write it now for du1, dv1 up to dum, dvm. So m is the cardinality of our gigantic set lambda. And they have an anti-commuting product. Which just means that when you write down a bunch of differentials side by side, you have to pay attention to what order they're in. And if you switch the order of adjacent ones, then you pick up a factor -1. Now, a p-form is going to be a function of u and v. So that's u1 up to um and v1 up to vm, times a product of p differentials. Written in some order, multiplied together by the wedge product. Okay, so it could be u times du, u1 times du1, dv1, du2. That would be an example of a form, a 3-form. Or you could have a sum of these, and it would still be a p-form. So if you took a sum of two things with the same value of p, I would still call that a p-form. Now, the maximum degree that's possible is p equals 2m, because these differentials are anti-commuting. And so when I write them in a product, if I want to get something that's non-zero, they have to all be different. And there are only 2m of them altogether, so that's the most I can have. And this top form, so the form of any form of degree 2m can be written in the following form. Some function of u and v, that's u1 up to um, v1 up to vm, times du1 wedge dv1 all the way down to dum wedge dvm. And if the du's and the dv's weren't in that order, then I'll put them in the order, and that might affect the sign of f. But I can always do that, and I can always write them in this order. And I'll consider this order to be the standard volume form. In other words, this is the order that I really like the best when I have a form of top degree. Now, I want to define what it means to take the integral of a form. So here's the definition. So I'll write k as a form. K is a form. And the integral of k is most interesting in the case when k is a form of top degree, 2m, in which case I can write it as I did over there. And in that case, it will just be the value of the integral over R2m of f of uv du1 dv1 up to dum dvm, where this is just Lebesgue measure. So this is if the degree of k is equal to 2m. And if the degree of k is less than that, I'm just going to define the integral to be 0. Because I really want to be doing an integral over R2m, and if I don't have enough differentials to do the job, then I'm just going to say that it's 0. All right. Now I'm going to do some things which are just like what we did before, which is to each point in our set 1 up to m, we'll have a complex field. So there's going to be a phi x, which is ux plus ivx, and its complex conjugate is what you think it is. And there are forms that correspond to this. So this is exactly the same thing that I was doing before, except I'm now thinking of as part of this bigger picture. And I don't want to be writing these differentials all the time. And in fact, they're not very conveniently normalized because, as you remember, when I go from du dv to d phi bar d phi, I picked up a factor of 2i. And there are also some pi's floating around. And so I'm going to change the notation and define psi x to be a scalar multiple of d phi x, where that square root is some square root that's just fixed once and for all. And psi bar will be 1 over root 2 pi I. Same square root. I don't take the conjugate of this constant, d phi x bar. So these are the fermions. Then psi x bar times psi x. There's secretly a wedge product in between them, but I don't want to write the wedge products all the time. Okay, so whenever we're multiplying psi's or d phi's, there has to be a wedge product because that's the only way that they're multiplied in this algebra. So that's we've already seen that d phi bar d phi was equal to 2i times du dv, and so the 2i will cancel the 2i that comes out of the bottom here, and so there's going to be a 1 over pi, and this will be dux dvx. So we can go back and forth between the du, dv, Lebesgue integral type thing and the psi notation. Now, suppose I have an m by m matrix A, which should remind you of the matrix A that showed up in the previous Gaussian integrals that we were discussing. I want to define what's called an action. S sub A is phi A phi bar plus psi A psi bar. So here I'm adding a 0 form, phi A phi bar, which is the same thing that it was before. It's the matrix product of the vector phi and phi bar in the matrix A, together with a 2 form, which is this linear combination of d phi's and d phi bars. Okay, again, it's a matrix product. So this is a definition. If I write it out in detail, it would be the sum over x and y from 1 up to m of phi x, axy, phi y bar, plus the same thing for the size. But there's really a wedge product multiplying the size there. There's an interesting special case that we'll need later on where A takes on the simplest imaginable form. So let's consider the special case where we fix some x in 1 up to m, and we take A to be the matrix A uv is equal to delta ux delta vx. Kronecker delta. Yes? There's a wedge product in here. No, there's a 2i. There's the factor of 2 that you're worried about is canceled by this 2. d phi bar x, d phi x turned out to be 2i dux dvx. Right? Is that what you mean? You mean this? Yeah, okay. Yes. So I want to consider this special case where A is 0 unless U equals X and V equals X. Then in this product, almost all of the terms disappear. Then for this particular A, SA simply becomes phi x bar plus psi x bar. And I'm going to give this the name tau sub x, because this particular form is one which is going to show up later on as well. All right, we're going to need to consider functions of forms. So, yes? Delta ux, delta vx. That's right. U has to be x and v has to be x. So in this sum, A is equal to 0 except for the term xx. And so I pick up phi x bar, and psi x bar, and all the rest are gone. So A is it's full of zeros. There's only one non-zero entry in the entire matrix A, which is the XX entry. So functions of forms. Let's suppose that I have a set of forms indexed by some set capital J. So each kj is a form. It's a linear combination of differentials with functional, whose coefficients are functions of the variables. And let's suppose that each kj is even. So an even form is a form which is a sum of p forms where each p is even. All right. I like even forms because if I multiply two even forms together, it doesn't matter what order they're multiplied in, because the anti-commutativity is going to be used an even number of times if you interchange the order. So when we're multiplying even forms, we don't need to worry about the order. And let's let kj0 be the degree 0 part of kj. The degree 0 part is just a function, okay, a function of u and v, or of phi and phi bar. It doesn't have any differentials in it. So a typical form, I mean, a generic form could have a degree 0 part. If it doesn't, then the degree 0 part would just be 0. Now, suppose that I have a function f that maps Rj, capital J, into C. And what I want to do is I want to define f of k. So k is not a j tuple of real numbers. It's a j tuple of forms. So I have to say what I mean by that. So suppose this is given. And suppose that I can differentiate that function as many times as I want. And then here's the definition of what we mean by the function of the form. It will itself be another form. And it's just defined in terms of the formal Taylor series for f about the degree 0 part of k. So it's going to be the sum over multi-indices alpha. So alpha has j components. And then we have 1 over alpha factorial. Take the alpha derivative of f and evaluate that at the degree 0 part of the components of k. And then you have a product, which I'll write k minus k0 to the alpha. So maybe I need to say a few things about what this is. So alpha is a multi-index. So alpha factorial is the product over j from 1 up to capital J of alpha j factorial. That's what this is. This is the partial derivative of f with respect to alpha 1 times with respect to the first coordinate, alpha 2 times with respect to the second coordinate, and so on. So I think that's self-explanatory. It's evaluated at a function. We're allowed to evaluate f at a real number, so we can compose it with the function k sub 0 in each of the components in the argument of f. And this product here, k minus k0 to the alpha, is defined to be the product over j in j of the form kj minus kj0 to the alpha j. And as I said, I was restricting to even forms so that I don't need to care about what order I write down the factors in that product. It won't matter. So maybe it would be nice to see an example. But before we come to the example, there's one general fact which is worth observing here, which is that these Taylor series, which are showing up, are actually always Taylor polynomials. Nice thing about forms. So these series always truncate because as soon as this product gets too big of a degree, more than 2m, if it has more than 2m factors, then it's going to be 0. So all functions of forms are polynomials as far as the fermionic part is concerned, as far as the size are concerned. So here's an example. Let's look at e to the minus tau x. So tau x was this form over here, phi phi bar plus psi psi bar, all evaluated at x. So the degree 0 part is this part. And there's a degree 2 part as well. So what we're supposed to do is we're supposed to expand out in a Taylor series of the non-degree 0 part, which is just the psi psi bar part. So what you would get is e to the minus phi x bar. That's the degree 0 part, which doesn't get expanded out. And then you would expand out the e to the minus psi psi bar part. And that's going to give you 1 minus psi psi bar plus 0, because all of the other terms are going to vanish, because psi squared is equal to 0. So this is a rather extreme example of a function being a polynomial, just a linear polynomial. We'd also be interested in e to the minus sa in general, not just for this particular very simple a that has only one non-zero entry, but a general a has a degree 0 part, which is this phi a phi bar part, that will not be expanded, and then we expand out the psi a psi bar part in a Taylor series. And so this is going to be e to the minus phi a phi bar, and then there'll be a sum, n equals 0 to infinity, of minus 1 to the n over n factorial times psi a psi bar to the power n. But it doesn't go all the way to infinity because of what I was just saying. The biggest power that you can have here is n equals m, which is the size, the cardinality of the index set that we're dealing with, because if it's any bigger, then you have repetitions of psis and psi bars. So this sum really only goes up to m. Yeah, that's right, because the degree 0 part is sitting in here. Each time you differentiate, you leave the e to the minus phi a phi bar part alone. So these are definitions. You haven't quite seen yet where all of this is going. But here's a rather interesting fact. This example is called self-normalization. It says, suppose I'm given any a which has a positive definite Hermitian part. Then, so if a has a positive definite Hermitian part, then the integral of e to the minus sa is equal to 1. You don't need to put a 1 over z in front to normalize it. It normalizes itself no matter what a is. It's got a built-in normalization. So here's the proof. We want to compute the integral e to the minus sa. So e to the minus sa is a form by definition, right? It's a form. Here it is. And, well, the definition of integrals of forms that I gave said the integral of a form is 0 unless it's of top degree. So the only thing that we retain from this entire expression when we want to do the integral is the top term. The rest all integrate to 0. They just don't have enough differentials. So there's only one term from that Taylor expansion which gives us non-zero result here, and it's this one. So e to the minus phi a phi bar, and 1 over m factorial minus 1 to the m times psi a psi bar to the m. That's the way I define the integral. Now let's convert this to a Lebesgue integral, because ultimately if we want to evaluate an integral, we have to turn it into a Lebesgue integral. So I have 1 over m factorial. There's a minus 1 to the m. Remember, there was these factors root 2 pi I inside the psi's when they were converted to d phis. So there's going to be 1 for psi, 1 for psi bar. So together they'll give me a 2 pi I for every psi a psi bar, for every psi psi bar. And so then I will have the integral over R2m of e to the minus phi a phi bar times d phi a d phi bar to the power m. So we need to convert this d phi a d phi bar to the power m into a 2m dimensional Lebesgue integral. And this is where the anti-commutation comes in a big way. So let's isolate that interesting part of the integrand, which is going to give us all our differentials, and work out what it is. So each factor here is a big matrix product, so there's going to be a sum over x and y for each factor in the product. There'll be m of them all together. I'll put them out in front, x1, y1, up to xm, ym. And then there'll be all the matrix entries. Those are just scalars. We don't need to worry about their order, but for the d phis we do. So there's a d phi 1, d phi 1 bar, up to d phi m bar. I mean, we don't need to worry about the order of the pairs, but we need to worry about the order within a pair. D phi 1 bars minus the other way around. And, sorry, these are not ones. These are x1s, y1s, and xm's, ym's. They're not in order yet. They're just in the order that they come in our matrix products. But I can put the x's in order just by shuffling pairs around. And that won't cost me any minus signs. So I'll just put the x's in order, and then I'll relabel the y's. So there are going to be m factorial ways of permutations of the x's. And then I'll have the sum over y1 up to ym of a1, y1 up to am, ym, d phi 1, d phi y1 bar, d phi m, d phi ym bar. Okay, so these y's are new y's compared to the old ones, but they're just some dummy indices here. I'm just saying that I can rearrange the pairs without changing anything, and so I'm going to put the pairs so that their first index is in order, and there are m factorial ways of doing that, and I don't have to sum over the x's anymore because that's taken care of by the m factorial. And of course, I want the x's all to be different and the y's to all be different, because when I'm doing my integration, they have to all be different or I get 0. And if they weren't anyway, this would be 0. So now I want to put the y's in order. But when I put the y's in order, then I'm going to pick up a minus 1 every time I interchange two y's. So this is going to give me m factorial times the sum over y, 1 up to ym. Actually, these have to be distinct to get a non-zero value. Then there'll be the sign of the permutation of those. And then there'll be the ay1 up to am, ym. And then these guys will all be in order. And they form a common factor. And this is just the determinant of A. And this factor here is 2i to the power m times our standard volume form. That's the standard volume form that we need in order to ultimately do our Lebesgue integral. So we've been working on this factor, and we've just computed it here. And look, there's an m factorial that cancels the m factorial over there. Was this 2i, or there should be a, am I missing a pi? Where's the pi? Oh, I want the pi. Sorry, I want the pi. Okay, so what do we get? Let's just write everything down. We have 1 over m factorial minus 1 over 2 pi I to the m. And then we have the integral over r to m of e to the minus phi a phi bar. And then, actually, I think I don't want to write it this way. I'm just going to leave it as d phi 1. I do want it in the other order, though. I want to change the order for each factor, which will cost me minus 1 to the m. And then there's the determinant of a, and there's m factorial. Am I missing anything? This step I didn't do. I think everything's in order here. So the m factorials go out, and the minus ones go out. And this is what we called ZC. So this is det A over 2 pi I to the m times ZC. And ZC was the reciprocal of the prefactor. So that completes the proof. These integrals are self-normalizing. If you do the integral of e to the minus sa for any a that you're allowed to integrate in this way, then you get 1. And there's an amazing extension of this. So for a is above, m by n matrix with positive Hermitian part, and f any function on Rm, complex valued, which is nice enough. It can have small exponential growth would be OK at infinity. Then the integral of e to the minus sa f of tau. So this f of tau you should think of as f of tau 1 up to tau m. And tau sub x was phi x bar plus psi x bar. It was that form. So I'm taking a function now of m forms. It's the m components, tau at every point in our space. And that was defined. And so this is a form. This is a form. I can multiply the forms together. They're even forms, so everything's OK. Don't need to worry about sign. This just turns out to be f of 0. Let me just sketch the proof for you in a line or two. I mean, it's basically the proof. You can turn it into the proof. You just have to dot some i's. I want to suppose that f is nice enough that I can write it as in terms of its Fourier transform. So I want to suppose that f of t is a vector in Rm, can be written as the inverse Fourier transform of its Fourier transform. So tau here is a vector tau 1 up to tau m. And tau x is phi x bar plus psi x bar. So write f in terms of its Fourier transform. I guess it's just an integral over Rm. I have only m. So do that. Then write the integral e to the minus sa f of tau. You have to apply this formula also to tau, but that works out. And then apply Fubini. So you have to justify these things, but the formalism is a good one, and these things work out. So we will have that. Then we'll have the integral of e to the minus sa, which was already sitting there. And then there's going to be, now this t becomes a tau. So I'm evaluating this formula at tau and plugging it in. So I will have minus I v dot tau. It is. Yeah, these are just functions of Rm. But I'm claiming that you can also write it for forms. And if you do write it for forms, then you're going to get this formula. Now, remember so this v dot tau is just sum over x of phi x vx phi x bar plus psi x vx psi x bar. It's like a phi a phi bar where a is diagonal with entries v. In fact, iv here. So this is the same as what I would write minus sa plus iv. Now a plus iv, or write it if you want capital V, where capital V is the diagonal matrix whose entries are the little v's. This is just an example of what we were dealing with over there, but with a new a. I haven't changed the fact that it has positive Hermitian part because iv is not part of its Hermitian part. And so this integral is just 1. But then we're taking the inverse Fourier transform and evaluating it at 0. And so we just get f of 0. OK, so there's 5 minutes left, and maybe that's enough to prove the representation that I was hoping to get to today, which is to get rid of the loops. So to show how this formalism that I've spent the last however long it's been talking about will get rid of the loops that showed up when we didn't have the fermions but only had the bosons. Now I want to get a generating function for self-avoiding walk paths without any loops in the background. Now, to do that, I have to claim that integration by parts extends to this setting. And the way that that happens is a formula like this, that if I take the integral of phi a bar e to the minus sa times f, or let's write it this way, maybe it's better, f times e to the minus sa, that's equal to the sum over x from 1 up to m of cax integral df by d phi x e to the minus sa. So it's the same kind of formula for Gaussian integrals that we had when we had integration by parts previously. And it just works the same way. In fact, the proof relies on the other proof as well. Now I can come to the main theorem for today, which is that for xy in 1 up to m, which I'm thinking of as my big set lambda, if I do the integral e to the minus sa times phi a bar phi b product over x not equal to a and b of 1 plus tau x. Previously, we had 1 plus phi x bar, but now There's a psi x bar that's inside the tau x, and there are also some psi's up here in the exponent. And together, the psi's up in the exponential and the psi's that are down here in the product are what produces ultimately a Lebesgue integral when you expand everything out. But the claim is that this is equal to the sum over all self-avoiding walks from A to B in our set lambda of c to the omega. And no loops in the background. So in our previous representation, we had an expression like this, and then there was an integral which ended up producing loops when we decomposed the permanent over cycles and so on. I claim that doesn't appear here. And, well, the proof is exactly as before, except something nice happens. So we just apply integration by parts repeatedly. The e to the minus sa just sits there in the integration by parts, right? So the phi a bar contracts with what you get by differentiating with respect to phi a, with respect to another phi in this product. So you can either differentiate here or you can differentiate in there. And what will happen is that the left-hand side becomes equal to the sum over self-avoiding walks from A to B of c to the omega, just exactly as before. But there'll be something left over, which will be terms where you have something which is not differentiated in here. So there's going to be the product over x in, let's call it lambda, minus ab, no, not minus omega, of 1 plus tau x e to the minus sa. It's exactly the same application of integration by parts that we used before. The tau x is now playing the role of the phi x bar, but the psi x bar, which is inside tau, is not noticed by the differentiation process that takes place in the integration by parts. And now we're done because this integral is 1. Because this is a function of tau. And this extension over here says that if you want to integrate with respect to this exponential factor, a function of tau, all you do is you evaluate the function at tau equals 0. And if you evaluate this function at tau equals 0, then the product, it becomes 1. Okay, so QED. So by going to this kind of more exotic setting of introducing these fermions and this sort of theory of Gaussian integration, which involves differential forms and functions of differential forms, we end up having a way of taking something that we might be interested in here, like the generating function for self-avoiding walks on a finite set, but the set could be very, very large. And we can study limits. That's the topic of the tutorial today. We can write that in terms of an integral. There's a corresponding integral representation that I'll mention tomorrow for the case of a weakly self-avoiding walk, actually a continuous time version of the weakly self-avoiding walk, which is a little more convenient to work with, and that's the one I'm going to discuss in more detail tomorrow. So there's another representation that instead of taking these strictly self-avoiding walks, takes a version of continuous time weakly self-avoiding walk and writes it as an integral like this, which is more convenient for analysis. And what I'll describe tomorrow is how you can apply then renormalization group methods in order to analyze this integral on Z4 and prove that the critical 2-point function has behavior 1 over x squared for large values of x. And I'll stop there. Thank you.